James Webb looks into the oldest reachable light, where galaxies should still be small, faint, and only beginning to assemble, yet in deep infrared fields. A few sources appear brighter and more compact than simple expectations allow, as if too much structure forms too quickly. Some of the tension softens when emission lines, dust, lensing, and selection effects are measured more carefully, but a handful of candidates still keep the question open. This video follows the evidence step by step, from redshifted starlight to confirmed spectra, showing what is solid, what is uncertain, and what Webb may be revealing about the first galaxies. If this calm journey through cosmic dawn helps the mind unwind, a like and a subscription support the channel and bring more sleep-friendly science documentaries like this one. At the farthest edge of what James Webb can presently turn into a measured early universe scene, the mystery begins not with one galaxy, but with a viewing window. Webb is an infrared telescope, and infrared light is stretched light, light whose wavelength has been pulled longer by the expansion of the universe during its travel across cosmic time. Because of that stretching, some of the earlier starlight no longer arrives mainly as visible light. It reaches modern instruments shifted into the infrared, where Webb is designed to work. NASA explains that Webb is engineered to observe the earlier stages of galaxy formation and is capable of revealing stars and galaxies that existed only a few 100 million years after the Big Bang. In this sense, the first region of the mystery is observational rather than material. It is the outermost horizon of light that a human-built telescope can still gather, separate, and turn into evidence. This horizon is not a wall. It is a limit shaped by time, expansion, faintness, and instrumentation. Light from the early universe travels for more than 13 billion years before it reaches the telescope. During that time, cosmic expansion stretches the light and makes the sources appear dimmer and redder than they were when the light first left them. NASA's overview of Webb's early universe science describes this simply. The telescope is essentially seeing objects as they were when the light first departed, and the great distance means that the universe itself has altered the light on the way here. The farther back astronomers try to look, the more demanding the work becomes. The galaxies are tiny on the sky, their light is weak, and every reliable claim depends on long exposures, careful filtering, and eventually spectroscopy, the splitting of light into its component wavelengths. At the horizon window, astronomy becomes a practice of patience. What appears through this window is not yet the fully grown cosmic landscape familiar in the later universe. NASA's early universe material says Webb can reveal stars and galaxies only a few 100 million years after the Big Bang. In an era when galaxies are beginning to assemble and cosmic structure is still young, before Webb, the expectation is not that nothing should be there, but that what is there should often be small, faint, and difficult to detect. A young universe has had less time to gather gas, form stars, merge galaxies, and build heavy structure. Farther distance means earlier time, and earlier time means a cosmos that should still be in comparatively early stages of assembly. When the telescope looks through this window, the broad hope is to catch the first clear stages of growth. Webb does reach remarkably far into that early time. NASA reports that JAD's GS Z14-0 is seen at less than 300 million years after the Big Bang, that JADS-GS-Z13-1 is observed at about 330 million years after it, and that MOM-Z14 is seen at about 280 million years after it. These ages matter because they place real measured galaxies very near the beginning of the era, in which galaxies first become visible in substantial numbers. The outermost horizon is therefore no longer a blank theoretical zone beyond reach. It contains confirmed galaxies whose light has actually been captured and whose distances have been spectroscopically measured. The existence of that population is one of Webb's great successes. At the same time, it is the opening through which the present mystery enters. The title's sense that something does not add up begins here. At the level of simple seeing, NASA and ESA both note that Webb is finding more bright galaxies in the young universe than many astronomers expected before launch. Some early candidates appear so luminous that they seem difficult to reconcile with many pre-Webb assumptions about how quickly galaxies could form stars and assemble mass. The first shock is therefore not buried deep in one technical parameter. It arises in the basic act of observation. When the horizon window opens, it does not reveal only the faintest expected traces of first structure. It reveals a sky that, in some surveys, appears more crowded with bright early galaxies than many researchers had prepared for. The mystery is born at the boundary between expectation and count. That boundary must be handled carefully. NASA also emphasizes that this is not a simple story of the standard cosmological model collapsing at first contact with better data. Later Webb analyses show that some of the earliest claims of impossibly massive galaxies soften when astronomers account more carefully for how black holes, emission lines, and very young stellar populations can make galaxies appear brighter than a simple stellar mass estimate would suggest. Even so, NASA states that Webb still finds roughly twice as many massive galaxies in the early universe as some theoretical predictions expect. This makes the horizon window especially important. It is not merely producing sensational anomalies, it is producing a more disciplined tension, one in which the gross outline of cosmic history remains standing while the details of very early galaxy growth require adjustment. So the first region of the mystery is a window made of stretched light. It sits at the outer edge of present observation, where infrared astronomy turns extreme distance into an imageable past. Through that window, Webb now sees confirmed galaxies from less than 300 million years after the Big Bang, and a broader population from only a few 100 million years after it. The puzzle does not yet lie in one internal mechanism inside those galaxies. It lies first in the fact that the window opens so clearly onto a young universe that already seems unexpectedly full of visible structure. At the horizon itself, the contradiction is still gentle. The telescope looks farther back than before, and what it sees is real. The unease begins because the earliest visible scene already appears richer than many astronomers expected when the window was still only a hope. Around the earliest galaxies there is not, at first, a clear and open cosmic sea. There is a fog. The word is only an image, but it is useful, because the outer environment of the young universe is filled with neutral hydrogen gas that blocks and scatters some of the light astronomers most want to see. Neutral hydrogen means a hydrogen atom whose single electron remains bound to its proton. In the long early period after the first free light of the cosmos begins to travel, the gas between galaxies is largely in this neutral state. NASA explains that rionization is the process in which that neutral hydrogen is later converted back into ionized hydrogen by the first stars, galaxies, and black holes, and that this transformation occurs between about 150 million and 1 billion years after the Big Bang. Before that clearing is complete, the outer environment is not empty transparency. It is a dim intergalactic medium that still resists the passage of certain forms of light. The fog matters because astronomy at these distances is not only a matter of finding faint objects, it is also a matter of asking what the space between those objects allows to pass through. If the intergalactic gas remains mostly neutral, then some ultraviolet light from young galaxies is readily absorbed before it can travel far. NASA describes the early universe as being immersed in a fog of neutral hydrogen gas for much of its first billion years. In that state, the universe is not dark in the sense of containing no sources of light. It is dark in the sense that light has trouble moving freely through the surrounding medium. Ionization slowly changes this condition. As the first luminous objects pour energetic radiation into their surroundings, the hydrogen atoms are stripped of their electrons and become ionized again. Ionized gas is more transparent to the relevant radiation, so patches of clear space begin to open. NASA's descriptions of reionization often compare it to a haze lifting, and the image is apt because the process is uneven. The early universe does not switch from opaque to transparent everywhere at once. Instead, bubbles of ionized gas form around the first sources of ultraviolet light. Those bubbles expand into the neutral surroundings and eventually merge. In older NASA language, the clear regions increase in size until neighboring regions join and clear up the fog of neutral hydrogen. This detail is important because it means visibility in the early universe is patchy before it becomes general. A galaxy may exist and may even be bright, while still sitting inside or behind enough neutral gas to make parts of its light very hard to detect. Another may happen to lie in or near a cleared region, and therefore reveal itself more readily. The outer environment is therefore not just background. It actively controls what kind of early universe can be seen. This is one reason the recent Webb findings feel so striking. NASA reports that the galaxy JADES-GS-Z 13-1, seen only about 330 million years after the Big Bang, shows bright Lyman alpha emission from hydrogen, and that this is surprising because such emission should have been absorbed by the dense fog of neutral hydrogen thought to fill the early universe at that time. Lyman alpha is a specific wavelength of light emitted by hydrogen atoms, and it is especially useful for tracing young galaxies and the gas around them. But it is also fragile in a neutral environment. If the surrounding intergalactic medium is still foggy enough, that light should be scattered out of the line of sight or absorbed. Its appearance at such an early time therefore suggests either that the surrounding fog has been cleared more effectively than many astronomers expected, or that the local conditions around the galaxy are more favourable than broad averages imply. NASA's more recent Webb results strengthen that impression by showing that early galaxies can play a larger role in clearing space than many simple pictures assume. In June of the year 2025, NASA reports that Webb uncovers a population of faint galaxies likely driving cosmic reionization, and again emphasizes that for much of its first billion years, the universe is immersed in neutral hydrogen fog. This turns the outer environment into a dynamic field rather than a passive veil. The gas between galaxies is not merely waiting to become transparent, it is being changed by the galaxies themselves. The first galaxies are not only sources of light seen through the fog, they are among the things that lift the fog. The fog also gives the early universe a slow quality. Reionization is not over in a brief instant. NASA places it across a very broad span of cosmic time, from roughly 150 million years after the Big Bang to about 1 billion years after it. That means the Great Clearing is not an event but an era. During this era, different regions of space can be in different states. Some are more transparent, some less. Some galaxies may already be contributing strongly to the ionization of their neighborhoods, while other regions remain largely neutral. Seen this way, the mystery that does not add up becomes gentler and more physical. It is not only that some early galaxies appear bright, it is that their brightness is being measured through an environment that should still be difficult for light to cross. The outer region around them is supposed to be thick with neutral hydrogen. Yet in at least some cases the light arrives with signs of having crossed a surprisingly clear path. Observations indicate that reionization is indeed underway early, and that galaxies are central to it. It remains uncertain exactly how quickly the first transparent bubbles grow, how large some of them become at very early times, and how representative the clearest cases are of the broader cosmos. What is already clear is that the first galaxies do not live in empty blackness. They live in a transforming fog, and that fog is part of the reason their light now feels so unexpected when it reaches Webb. The next outer region of the mystery is not a galaxy, but a patch of sky. James Webb does not discover the early universe by sweeping the whole heavens at once. It works through deep fields, very small, carefully chosen areas where the telescope can stare for long periods and gather faint light that would otherwise remain below detection. NASA and STSCI describe the JWST Advanced Deep Extragalactic Survey, known as JADES, as one of the largest early Webb programs, built to uncover and characterize faint distant galaxies through deep infrared imaging and spectroscopy. This matters because the tension in the early universe does not first appear as a lone, strange object. It appears when the same small region yields source after source from the first billion years of cosmic history. The survey field becomes a patient counting ground. These fields are chosen with care. JDS observes the well-studied Goods South and later Goods North regions, areas already examined deeply by Hubble and other observatories. NASA says the JD's NIRCam image shows a portion of Goods South, and that more than 45,000 galaxies are visible there. The point is not that all of these are extremely ancient. The point is that the survey field is already rich with known structure, calibration history, and comparison data. A deep field is therefore not random darkness. It is selected darkness. Darkness whose faint contents can be measured against years of prior work. Webb enters those fields with stronger infrared sensitivity and begins to pull out galaxies that earlier telescopes could not see clearly enough. The smallness of the field is part of the method. A narrow region allows very long exposure times and repeated imaging in different wavelength bands. NASA notes that the JADES field is observed in 9 infrared wavelength ranges, and STSC Sunday describes JADES as devoting about 32 days of telescope time to uncovering and characterizing faint distant galaxies. Another STSCI archive page describes JADES as the largest deep survey program in Webb's first years, and says it will cover over 100 square arc minutes in the near-infrared while producing thousands of galaxy spectra. This is why the field acts less like a photograph and more like an excavation. The telescope is not glancing, it is digging. Each additional hour turns a blank patch into a denser record of distant sources. In these survey fields, the mystery begins to change shape. A single, very distant galaxy can always be treated cautiously as an exceptional case. But when a field yields many bright early candidates, the discussion shifts from anomaly to population. NASA's early universe explainer says Webb is capable of revealing the general population of stars and galaxies that existed only a few 100 million years after the Big Bang. That phrase, general population, is important. It means the telescope is no longer dealing only with one record breaker. It is starting to reveal what the young universe looks like statistically in selected deep fields. Once the problem becomes statistical, it also becomes harder to dismiss. The question is no longer whether one unusual source exists. The question is whether the whole counted population is brighter, more numerous, or more mature than many pre-launch expectations suggest. JADES is not alone in this work. NASA's SEERS material reports that the Cosmic Evolution Early Release Science Survey identifies 7 galaxies from when the universe is only about 540 million to 660 million years old. SEERS therefore help show that the early tension does not belong to a single observing team or one isolated field. Different Webb programs, using different parts of the sky and different observing strategies, are all beginning to reveal ancient galaxies in meaningful numbers. The exact age range and source selection differ from survey to survey, but together they turn the distant universe into something that can be sampled rather than merely glimpsed. A field becomes a census region, and the census begins to feel unexpectedly full. There is a quiet discipline in this approach. Deep fields do not produce instant certainty. They produce candidates first, then improved imaging, then spectroscopy, then revision. NASA's blog on JADES-GS-Z14-0 explains that the team first searches Webb images for faint galaxies visible in the infrared whose spectra appear to cut off at a critical wavelength. That cutoff is later tested with spectroscopy. The survey field therefore acts as a filtering machine. It gathers many red distant-looking sources, then sorts them into stronger and weaker cases. Some candidates are confirmed, some are revised, and some turn out to be less extreme than first thought. This process is part of why the current mystery feels scientifically solid, rather than merely sensational. The same fields support both bold claims and later correction. The deep field also changes the meaning of cosmic emptiness. A patch of sky that appears blank to the eye and sparse in ordinary telescopes becomes crowded under Webb's infrared stare. NASA's JADES material says the good south field alone contains about 1,000 galaxies from the universe's first billion years within the studied region. That does not mean the early cosmos is already fully mature. It means the carefully chosen survey field is capable of turning faint ancient light into a visible demographic record. Once that happens, the outermost region of the mystery becomes less about distance itself and more about abundance. The problem is no longer simply that Webb sees far. It is that in seeing far, it also begins to see enough objects to challenge older expectations about how quickly visible structure should emerge. This is why the survey field is the right next region after the reionization fog. Before attention narrows to the record galaxies themselves, astronomy first needs a place where those galaxies can be found in numbers. JADES and SEERS provide that place. They turn deep time into mapped territory, not by making the early universe easy, but by making it countable. The field holds the young galaxies inside one shared observational frame. It lets astronomers ask not only what one object is, but how many similar objects appear nearby in time and space. Once that question is asked, the tone of the Webb mystery changes. It becomes a problem of population, brightness, and frequency emerging from survey design itself. So this outer observational region is a rectangle of sky, chosen in advance, stared at for weeks, and filled slowly with ancient light. It is not large on the sky, yet it becomes large in meaning. Inside it, the early universe stops being only a remote idea and begins to appear as a measured population of galaxies from the first billion years. JADES, SEERS, and the other deep surveys do not solve the puzzle by themselves. They do something quieter and more powerful. They establish that the puzzle is not accidental. The telescope keeps looking into these fields, and the fields keep yielding early sources in enough numbers to make the discrepancy feel real. In the darkness of a carefully chosen patch of sky, the mystery begins to acquire weight. Inside the deep survey fields, the first clear points of the early universe mystery resolve into individual galaxies with names, distances, and measured ages. NASA reports that JADES-GS-Z14-0 is confirmed at a redshift of 14.32, making it the most distant known galaxy at the time of that report and placing it less than 300 million years after the Big Bang. NASA also reports that JAD ES-GS-Z 13-1 is seen at about 330 million years after the Big Bang, while the more recent object MOM-Z14 is shown by Webb only about 280 million years after the beginning of the universe. These are not vague suggestions at the edge of detectability. They're confirmed or reported record-breaking ancient galaxies that now give the outermost visible cosmos a set of concrete landmarks. The horizon window no longer opens only onto anonymous faint smudges. It opens onto named systems whose light has crossed almost the entire age of cosmic history. That change matters because one distant object can be treated as a rarity, but several record breakers in close succession begin to feel like a pattern. NASA's report on JADES-GS-Z14-0 explains that over the previous 2 years, Webb has been exploring what astronomers call cosmic dawn, the first few 100 million years after the Big Bang when the first galaxies are born, and that the new record holder joins a rapidly growing set of galaxies found in this era. The telescope is therefore not merely stretching the old record a little farther. It is repeatedly turning what was once theoretical early territory into a populated observational domain. Each confirmed source makes the young universe seem less empty and more structured than it once appeared. The emotional effect is simple, even if the science remains careful. The earliest visible cosmos is no longer a lonely frontier with one exceptional beacon. It is starting to look like a place where galaxies are already present in meaningful numbers. JADES-GS-Z14-0 has special weight because NASA says it is not only record-breaking in distance, but also unexpectedly substantial in appearance. The source is found to be extended, measuring more than 1,600 light-years across, which means it is not simply a point-like object dominated by one compact central black hole. NASA says the light appears to be produced mostly by young stars rather than by emission from an active black hole. That makes the object especially important for the mystery. If the earliest record breakers were mostly tiny compact black hole-powered sources, one set of explanations would immediately rise to the front. But a galaxy that is spatially extended and dominated mainly by starlight is harder to dismiss as a simple imposter. It begins to look like a real young galaxy that has already assembled enough luminous structure to stand out far earlier than many astronomers once expected. JADES-GS-Z13-1 offers a different kind of surprise. NASA reports that this galaxy is observed only about 330 million years after the Big Bang, and yet shows bright hydrogen emission, of a kind that should have been strongly suppressed by the surrounding neutral hydrogen fog if the intergalactic medium were still as opaque as many broad pictures of that time suggest. This does not necessarily mean the whole universe is already transparent then. NASA's wording is more careful. It suggests that the galaxy may be mysteriously clearing the fog around it, or that its local environment is more open than expected. Even so, the significance is clear. A record galaxy this early is not only present, it is also illuminating the conditions of the space around it in a way that seems surprisingly advanced. The first visible galaxies are not just existing. Some of them may already be reshaping their surroundings. MOM-14 pushes the horizon still farther inward toward the beginning. NASA's January 2026 report says, Webb shows this galaxy as it appeared only 280 million years after the universe began. That figure places it even earlier than JADES-GS-Z14-0. In practical terms, the difference between 280 million and 290 or 300 million years is not the main point. The deeper point is that Webb keeps finding galaxies in an era that had only recently seemed almost beyond realistic confirmation. Each new record makes the observational frontier less speculative and more crowded. The telescope is not merely touching the edge once. It is repeatedly finding luminous systems near the same early interval. That is one reason the title's sense that something does not add up feels so persistent. The record keeps moving, but the underlying surprise remains. The young universe is visibly active very early. The confirmed record galaxies also change the role of skepticism. Before spectroscopy, a very red source in a deep image can still be only a candidate. Dust, unusual colours, or measurement noise can complicate interpretation. But NASA's blog on JADES-GS-Z14-0 emphasizes that the galaxy is spectroscopically confirmed, and the same general pattern of confirmation applies to the strongest record claims in this early universe discussion. A spectrum is light separated into wavelengths, and in this context it provides the decisive distance information by showing where key features of the source's light have been shifted by cosmic expansion. Once a record source is spectroscopically secured, the conversation moves away from whether it is really that distant and toward what such a distant galaxy is doing there in that form. The mystery sharpens because uncertainty in distance begins to recede. Yet the record galaxies do not by themselves prove that cosmology has failed. NASA's later discussion of early bright galaxies is more restrained. It says that some of the earliest claims of impossibly overmassive galaxies soften after astronomers account for light from accreting black holes and for the effect of strong emission lines and very young stellar populations. Even after those revisions, NASA still says Webb finds roughly twice as many massive galaxies as some predictions expect. This matters here because the record galaxies are best understood not as isolated evidence that everything is wrong, but as the brightest edge of a broader statistical tension. They are the most visible members of a population problem, not magical exceptions floating outside science. The mystery, therefore, remains serious without becoming uncontrolled. The data require repair of assumptions and models, but not abandonment of all structure. In this region of the story, the universe is no longer only a horizon or a fog or a survey field. It becomes a set of actual ancient galaxies whose ages approach the opening few hundred million years of cosmic history. JADES-GS-Z14-0, JADES-GS-Z13-1, and MOM-Z14 are the first clear markers in that territory. They are what the mystery looks like before it is broken into questions about brightness, mass, black holes, and star formation. They are simply there, very early, very distant, and now measured well enough that the first astonishment can settle into a more disciplined form. The outermost visible galaxies are no longer hypothetical, and their existence is the first solid reason the early universe now feels richer than many astronomers once expected. When the most distant confirmed galaxies are placed back into the wider population around them, the early universe mystery changes from a record book into a counting problem. The surprise is no longer only that a few galaxies exist extremely early. The surprise is that many of them appear brighter than many astronomers expected before Webb flew. NASA's first-year Webb summary says the observation nudged astronomers toward a consensus that an unusual number of galaxies in the early universe were much brighter than expected. This is a quiet but important statement. It does not describe a single spectacular outlier. It describes a population-level pattern, something repeated often enough across the deep fields that the surprise begins to feel structural rather than accidental. Brightness in astronomy is not the same as closeness. A galaxy can appear bright because it is near, because it is intrinsically luminous, because it is forming stars intensely, or because the observing band happens to capture especially strong emission from hot gas and young stars. In the deep early universe surveys, closeness is not the explanation. The galaxies are extremely distant and their redshifts are high. Their brightness is therefore the thing that requires explanation rather than the thing that explains itself. NASA's 2022 Webb report says the telescope is finding an unusual number of galaxies in the first few 100 million years that are much brighter than expected, and ESA's early Webb coverage similarly notes that the first observations reveal candidate galaxies in the very early universe that are brighter than expected and turn up in numbers higher than anticipated. The discrepancy begins at the most basic observational level. There seems to be more readily visible light from early galaxies than many pre-Webb models suggested. That matters because simple expectations for the young universe are conservative. A cosmos only a few 100 million years old has had relatively little time to gather gas into dense halos, cool that gas, form many generations of stars, and build large luminous systems. The earliest galaxies are therefore often imagined as small and relatively faint, not because astronomers think nothing forms early, but because rapid growth is hard. NASA's later discussion of the issue remains careful on this point. The agency says that some initial claims about impossibly massive galaxies soften after better accounting for how their light is produced, but it also says astronomers are still seeing more galaxies than predicted. The brightness tension therefore survives even after part of the first shock is moderated. The population itself still seems unexpectedly easy for Webb to find. The word population is especially important here. One object can be odd by chance. Several can still be treated as rare. But once deep surveys repeatedly uncover many bright sources at redshifts above 10, the question becomes whether the universe is making visible galaxies faster or more efficiently than many prior models assume. TSCI's public scientific summaries and talks on Webb results state the issue in simple terms: galaxies at redshifts above 10 are brighter and more numerous than expected. That phrasing is less dramatic than saying the standard model has failed, and it is more useful. It describes a specific tension that can be investigated. The telescope is not revealing chaos. It is revealing an early galaxy population whose abundance and apparent brightness are shifted upward relative to many forecasts. NASA's report on JADES-GS-Z14-0 captures the feeling of this moment well. The team says that when they first found strong evidence for a galaxy above redshift 14, they were wary because the source was surprisingly bright, something they would not expect for such a distant galaxy. That sentence is valuable because it comes directly from the process of discovery. The first reaction to some of these sources is not triumph alone, it is caution. The galaxies are so bright that astronomers initially wonder whether they might be blends, imposters, or somehow misleading. In other words, the brightness itself is part of what makes the detection scientifically unsettling. Webb is not merely finding the earliest galaxies, it is often finding them in a state of visibility that feels too generous. This is why the early mystery is best described as something that does not add up, rather than something that immediately breaks all theory. The data are strong enough to disturb expectations, but not so wild that every framework collapses at once. NASA's August 2024 summary says that although some early galaxies turn out to be less massive than first thought, Webb is still seeing more galaxies than predicted, and none of them are so massive that they break the universe. That sentence defines the current balance exactly. The problem is not gone, but it has changed character. What remains is an excess of early bright systems compared with many previous expectations. The disagreement is now narrower and more quantitative, but in some ways it is also more solid because it survives after the first wave of corrections. There is also a practical consequence to this unexpected brightness. NASA's first-year Webb account notes that if early galaxies are brighter than expected, it becomes easier for Webb to find more of them in later deep surveys. This means the brightness tension is self-amplifying in observational terms. A surprisingly visible early population leads to more detections, and more detections turn a surprise into a data set. The telescope does not remain stuck with one puzzling discovery. It gathers a sequence. Each additional bright early galaxy makes the counting problem more robust and less dismissible. The early universe starts to look less like a sparse frontier of rare first lights, and more like a landscape in which luminous systems are already common enough to reshape the statistical picture. So in this region of the story, the mystery is simply this. The young universe appears brighter than many astronomers expected it to be. Not brighter everywhere, and not in a way that forces one immediate conclusion, but bright enough, often enough, to create real tension between observation and prior intuition. NASA and ESA both frame the result in population language, and later NASA analysis confirms that the tension survives even after some of the first claims are softened. The early cosmos that Webb reveals is not empty, not merely faint, and not easy to fit into older expectations of slow visible assembly. It is a place where bright galaxies show up early and in sufficient numbers that their light begins to feel like a problem in its own right. At this point in the mystery, the question becomes more precise. The early galaxies are not only present and not only numerous enough to feel surprising, some of them also seem intrinsically bright, meaning bright in their own right rather than merely bright because of a simple observational trick. NASA's report on JADES-GS-Z 14-0 makes this especially clear. The team initially hesitates because the source is brighter than expected for such a distant galaxy. Yet follow-up work shows that it is not a tiny unresolved point, and not mainly the light of one central black hole. NASA says the galaxy is extended, measuring more than 1,600 light-years across, and that its light appears to be caused mostly by young stars rather than emission from a central supermassive black hole. That combination is what gives the brightness problem its weight. A very distant source is one thing. A very distant source that already looks like a real extended stellar system is another. The word intrinsic matters because astronomy is full of sources that can look brighter than they truly are in one simple sense. A compact active black hole can outshine much of its host galaxy. A foreground object can contaminate a distant one. Strong emission at certain wavelengths can make a galaxy appear more massive or more mature than it really is if the light is interpreted too quickly. In the first wave of Webb excitement, many astronomers worry about exactly these possibilities. The early bright galaxies might be less troubling if they are mostly powered by black holes, or if their light is being read in a way that overestimates the number of old stars already in place. NASA's later discussion of the issue reflects this caution. It says some early galaxies are initially interpreted as excessively massive, but later analyses show that some of this tension softens when the contribution from accreting black holes and other light sources is treated more carefully. Even so, the intrinsic brightness problem does not disappear. JADES-GS-Z 14-0 remains important precisely because it resists the easiest escape route. NASA's description says the source is extended and mostly stellar, which means it does not behave like a simple quasar-like point source whose great brightness can be handed over to black hole activity alone. its size also matters. More than 1,600 light-years is still small compared with mature later galaxies, but is large enough to suggest a real-built stellar system rather than a single compact engine masquerading as one. In the calm language of astronomy, this is a strong statement. It means that by less than 300 million years after the Big Bang, Webb is seeing at least one galaxy that already spreads its light over a measurable structure and shines strongly enough to disturb earlier expectations. That is why the mystery narrows here from simple counting to physical interpretation. If the earliest bright sources are truly galaxies dominated mainly by young stars, then the question becomes how such intense starlight is assembled so early. A young galaxy can be bright without being impossibly old if it is forming stars very efficiently, especially hot massive stars that emit strongly in the ultraviolet before the light is shifted into the infrared by cosmic expansion. NASA's reporting on early Webb results repeatedly points toward this possibility. The issue is no longer just whether the telescope is seeing too many galaxies. It is whether some early galaxies are producing visible starlight faster, or in more concentrated bursts, than many researchers had assumed before Webb. The brightness problem begins to look less like a violation of physics, and more like a sign that early star formation may be more efficient or more intense in some systems than older models allowed. Still, the tension remains real because early efficiency has limits. Time in the young universe is short. Gas has to collapse into dark matter halos, cool, fragment, and form stars. Radiation and stellar feedback can then push back against further star formation. None of this prevents galaxies from becoming bright early, but it does set a natural expectation that the first system should usually be small and comparatively faint. When NASA says Webb keeps finding more early galaxies than predicted, and when JADES-GS-Z 14-0 turns out to be both extended and predominantly stellar, the implication is that the earliest visible growth may be happening on the fast end of what many models previously emphasized. The mystery is therefore not that galaxies exist early. It is that some of them appear to be doing galaxy-like work at a surprisingly mature pace. There is also a methodological lesson in this section of the story. The more astronomers learn about these galaxies, the more the problem becomes subtler rather than simpler. Early headlines suggest objects that are impossibly massive and perhaps fatal to the standard picture. Later analysis trims that claim. Some sources are less massive than first feared once their light is interpreted more carefully. Yet trimming the first claim does not remove the puzzle of intrinsic brightness. In a way, it sharpens it. The galaxies may not be absurdly oversized in stellar mass, but some of them still seem genuinely luminous, genuinely early, and genuinely difficult to fit into the slowest pre-Webb expectations. The contradiction becomes narrower, but also more robust. It is no longer a broad alarm built mostly on first impressions. It is a more disciplined tension tied to real extended galaxies and the real starlight they seem to contain. So this region of the mystery holds steady in a calm but stubborn form. Some of the earliest galaxies are not merely visible by accident. At least in notable cases, they appear to be actual extended systems dominated mainly by young stars, shining from a time when the universe is still only a few 100 million years old. Observations indicate that part of the first mass crisis softens under better interpretation, but it remains uncertain whether all of the observed early luminosity can be comfortably explained by current assumptions about star formation, gas supply, and black hole contribution. What is already clear is that the early universe light in Webb's deepest fields cannot always be dismissed as simple illusion. Some of it belongs to real galaxies whose brightness, taken on its own terms, still does not add up as easily as many astronomers once expected. The next layer of the mystery is not about how far the galaxies are, and not even first about how bright they are. It is about what that brightness seems to mean for stellar mass. In astronomy, stellar mass is the amount of matter locked into stars inside a galaxy. Before James Webb begins returning its deepest early universe images, many astronomers expect galaxies only a few 100 million years after the Big Bang to be present, but still in relatively early stages of assembly. Then the first Webb detections arrive, and some of the galaxies appear so bright that a straightforward reading suggests they already contain very large numbers of stars. In that first moment, the problem seems severe. If the light truly comes mostly from stars, and if the standard methods of turning light into mass are applied without much revision, then some early galaxies look as though they've grown too much, too quickly, in too little cosmic time. NASA later summarizes this early reaction in vivid language, saying astronomers expect galactic pipsqueaks and instead seem to find objects that look more like Olympic bodybuilders. The language is informal, but the scientific issue is precise. The first mass estimates appear uncomfortably high for the age of the universe being observed. This kind of problem arises because light is being used as a proxy for mass. A proxy is an indirect measure, something observed directly that is then used to infer something harder to measure. In a distant galaxy, astronomers cannot simply weigh all the stars one by one. They infer the likely stellar mass from the amount and color of the light, together with assumptions about how stars form, how old they are, how much dust is present, and what fraction of the light comes from stars rather than from some other source. In mature nearby galaxies, these methods can work well when enough information is available. In the very early universe, the situation is more difficult. The galaxies are faint, young, chemically simple compared with the later galaxies, and often dominated by very recent stellar populations. That means the same observed light may correspond to less stellar mass than older, simpler interpretations first imply. The early Webb puzzle therefore becomes a problem of interpretation as much as of observation. The galaxies may not actually be as overbuilt as their first brightness suggests. NASA's August 2024 analysis makes this revision especially clear. The agency reports that some of the early galaxies first thought to be excessively massive are in fact much less massive than they initially appear. One reason is that black holes in some of these galaxies make them seem brighter and bigger than they really are. Gas falling toward a rapidly growing black hole can heat up and emit large amounts of light. If that additional light is not fully separated from the light of the stars, the galaxy can look as though it contains many more stars than it truly does. In that case, brightness is real, but the inferred stellar mass is too high. This does not make the galaxy unreal. It changes what part of the galaxy is responsible for the visible power. Some of the first weight of the early mass crisis therefore lifts when the light is read more carefully, and when compact red sources likely influenced by black hole growth are treated differently in the accounting. That revision is important because it narrows the mystery without removing it. NASA says that when these compact bright sources are removed from the analysis, the remaining early galaxies are not too massive to fit within the predictions of the standard cosmological model. This is a major shift from the first impression. It means the strongest version of the crisis softens. The early universe is not now best described as containing galaxies whose stellar masses immediately break the theory of cosmic evolution. The standard model does not collapse at this step. The first panic fades, yet the same NASA report is equally careful in saying that the puzzle is not gone. There are still more massive galaxies in the early Webb data than some predictions expect. The article says that astronomers are still seeing roughly twice as many massive galaxies in the early universe as the standard model would predict. This is a smaller tension than the first dramatic mass crisis, but it is still a real one, so the picture becomes more disciplined. The original question is whether galaxies are assembling stellar mass impossibly fast. The revised answer is that some of them are not as massive as first thought, because part of their brightness does not come from stars alone. But even after that correction, the census still appears high. There are still too many substantial galaxies too early, even if they are no longer absurdly oversized. That leaves astronomers with a quieter but stronger problem. The disagreement is no longer built mainly on a few extreme estimates. It survives after a first round of correction and becomes a genuine issue of number density. The number of galaxies of a given mass found in a given cosmic volume. In other words, the early universe may not be producing impossible giants, but it may still be producing significant galaxies faster or more often than many older models emphasize. NASA's wording captures this balance well. The article says there is no crisis for the standard model of cosmology, but it also says a less thorny problem remains. That phrase fits the present state of the mystery. It is less thorny because the most dramatic interpretation softens. It remains a problem because the observations still resist complete comfort. The early galaxies no longer need to be impossibly massive for the tension to matter. They only need to be somewhat too common, somewhat too developed, or somewhat too efficient at turning gas into stars to keep the disagreement alive. The result is a puzzle that becomes harder to dismiss precisely because it becomes less extreme. Exaggeration is easier to throw out. A moderate repeated mismatch is often more scientifically durable. This early mass build-up layer therefore marks a turning point in the Webb story. At first, the telescope seems to reveal galaxies that are far too heavy for their age. Then later analysis shows that part of this impression comes from reading too much stellar mass out of light that is more complicated than it first appears. The galaxies are revised downward. The crisis shrinks. But the count remains elevated, and the young universe still seems to contain more substantial galaxies than many astronomers once expected. Observations indicate that the strongest alarm softens. While the broader tension survives, it remains uncertain exactly how much of the remaining discrepancy will yield to better modelling of the light, better treatment of compact active sources, or revised assumptions about early star formation. What is already clear is that the first Webb puzzle about early mass does not vanish. It changes shape. It becomes less dramatic, more quantitative, and more difficult to ignore. A new population enters the early universe story as something smaller, redder, and in some ways stranger than the brighter extended galaxies already drawing attention. NASA says that in December of the year 2022, less than 6 months after James Webb begins science operations, the telescope reveals something never seen before in this form, numerous red objects that appear small on the sky, which scientists soon call little red dots. The name is simple and descriptive rather than interpretive. They are little because they look compact, red because their observed colours are strongly shifted and unusual, and dots because in the images they often appear as tiny concentrated sources rather than broad extended systems. What makes them important is not only their appearance, but their abundance and timing. They're not rare curiosities found once or twice. They show up in enough numbers to become a class. This class matters because it seems to belong to a specific era of cosmic history. NASA reports that a large sample of little red dots is drawn from multiple Webb surveys, and that nearly all of them existed during the first 1.5 billion years after the Big Bang. The same NASA report says their distribution is especially intriguing. They emerge in large numbers around 600 million years after the Big Bang and undergo a rapid decline in quantity, around 1.5 billion years after it. NASA's broader summary of Webb surprises repeats that they seem to appear around 600 million years after the Big Bang and rapidly decline less than 1 billion years later. This makes them feel less like a permanent kind of galaxy and more like a temporary phase. They are present strongly for a time, then fade from the census. The class therefore carries a sense of timing as well as form. It looks like an early universe phenomenon with a limited era of prominence. Their visual character is part of the puzzle. NASA's image description of little red dots says each source has a yellow-white circular core surrounded by a red fuzzy ring. That description is observational, not explanatory. It tells what the telescope sees, not yet what the object is. The compactness is especially important because these sources do not resemble the larger obviously extended galaxies that can more readily be described as early stellar systems spread across measurable structure. Little red dots sit closer to the border between galaxy and comet engine in the imagination of the observer. They are distant, bright, red, and physically small on the sky. That combination makes them hard to classify quickly. NASA says researchers are perplexed by their nature, by the reason for their unique colours, and by what they convey about the early universe. The class is therefore not only new, it is unresolved at a basic level. Another reason they matter is that they have no clear familiar analogue in the later universe. NASA quotes Dale Kochevsky saying that researchers do not see analogues of them at lower redshifts, which is why they have not been seen prior to Webb. Lower redshift here means later cosmic time, closer to the present, where galaxies are easier to study and usually easier to categorize. If little red dots had obvious modern equivalents, astronomers could more comfortably place them inside an already known evolutionary path. But the lack of clear analogues makes them feel like a class specific to the younger cosmos. They may be a phase that later disappears, evolves into something less distinctive, or becomes hidden inside better-known categories. For now, NASA's wording keeps the interpretation cautious. The objects are real enough to form a large sample, yet unlike enough to resist immediate placement in the ordinary catalogue of galaxy types. Their census also tells something about how Webb is changing astronomy. NASA says the large sample becomes possible in part because astronomers use publicly available Webb data and search across multiple surveys, beginning with CEERS and expanding to JADES and NGDEEP. This matters because little red dots are not produced by one narrow observing choice. They turn up across several major deep extragalactic fields. A class seen in one field might still be treated as a local oddity of the survey. A class found across multiple Webb programs becomes more robust. The dots therefore acquire weight through repetition. They belong to the same broad statistical shift that makes the early universe feel unexpectedly rich in visible structure, even if their physical nature remains uncertain. Their observational reality as a recurring population is already secure enough that NASA describes them as a newfound galaxy class, and one of Webb's major surprises. At the same time, the class is not yet fully understood as purely galactic starlight. NASA's January 2025 report says that about 70% of the targets examined spectroscopically show evidence for gas rapidly orbiting at about 1,000 kilometers per second, a sign of an accretion disk around a supermassive black hole. NASA therefore says that many little red dots are likely accreting black holes, also known as active galactic nuclei. This does not solve the class completely. It narrows the possibilities. The dots may not be ordinary compact galaxies powered only by stars. They may often involve a central black hole feeding on gas and contributing strongly to the observed light. Yet NASA still describes the population itself as perplexing, because the exact balance between black hole light, stellar light, dust, and geometry is still under active study. The class stays strange even when one important clue is added. This is why little red dots matter so much for the wider early universe mystery. NASA's August 2024 report on overly massive early galaxies says that when scientists remove these galaxies, dubbed little red dots, from the analysis, the remaining early galaxies are not too massive to fit within predictions of the Standard Model. That means the dots are not just another oddity in the field, they are central to the first big alarm about early galaxy mass. If they are counted as ordinary stellar systems, they can make the early universe look much more developed than expected. If many of them are instead compact sources dominated by black hole accretion, the mass crisis softens. The class therefore sits at a critical interpretive junction. It is both a new population in its own right and a key reason the earliest Webb data initially seemed so difficult to reconcile with prior expectations. So in this region of the story, the mystery takes the form of a newly discovered class with a narrow early epoch, unusual colours, compact appearance, and uncertain nature. Observations indicate that little red dots become common around 600 million years after the Big Bang, decline by about 1.5 billion years after it, appear unlike ordinary later universe counterparts, and often show signs of rapidly growing black holes. It remains uncertain whether all of them are governed mainly by accretion light, by dense star formation, or by some combination that changes from object to object. What is already clear is that Webb has not merely extended an old catalogue, it has revealed a population that was effectively hidden before, and that hidden population now sits near the centre of the reason the early universe still does not add up as neatly as astronomers once expected. Inside the strange population of little red dots, the mystery narrows again, this time from the appearance of the objects to the source of their light. A galaxy can look bright because it contains many stars, but it can also look bright because something in its centre is releasing energy far more efficiently than ordinary starlight alone. NASA's explanation of the recent Webb results says that black holes in some of these early galaxies make them appear much brighter and bigger than they really are, and that the galaxies first thought to be overly massive likely host black holes rapidly consuming gas. When gas falls inward toward a black hole, it does not usually vanish all at once into darkness. It forms an accretion disk, a fast-moving disk of hot gas circling the black hole before crossing the point of no return. Friction and compression in that gas release heat and light, making the central region shine intensely. In this way, a hidden black hole can change the apparent meaning of a whole galaxy. The galaxy is still there, but part of the observed brightness no longer belongs to stars alone. This matters so much in the early universe because light is being used to infer properties that cannot be measured directly. If a very distant source is assumed to be shining mainly because of stars, then its total stellar mass may be estimated too high when a substantial fraction of the light is really coming from a central accretion disk. NASA states this clearly in its August 2024 summary. The extra light from black hole growth can make it appear that these galaxies contain many more stars and hence are more massive than astronomers would otherwise estimate. This means the early mass crisis softens not because the galaxies disappear, but because some of their brightness is reassigned to a different engine. The light still reaches Webb, but its origin becomes more mixed. A distant source that first looks like a very heavy young galaxy may instead be a more modest galaxy with a bright energetic centre. The contradiction shrinks as the accounting improves. NASA's January 2025 report on little red dots strengthens this interpretation. That report says about 70% of the spectroscopically studied little red dots show evidence for gas rapidly orbiting at about 1,000 kilometers per second. a speed consistent with an accretion disk around a supermassive black hole. NASA then states directly that many of these objects are likely active galactic nuclei. An active galactic nucleus is the bright energetic center of a galaxy powered by matter falling onto a supermassive black hole. NASA's glossary explains that such nuclei appear much brighter than ordinary galactic centers because the black hole produces extra energy as matter in an accretion disk falls inward. This is an important turning point in the mystery. The unusual brightness of some early sources is no longer only a puzzle. It is increasingly tied to a known physical mechanism. The mechanism is familiar in the later universe, but Webb now finds evidence that it's also active very early in cosmic history. The timing of this black hole light is part of what makes it so consequential. NASA says little red dots appear in especially large numbers around 600 million years after the Big Bang, and decline rapidly by around 1.5 billion years after it. That suggests the early universe may pass through a phase in which compact growing black holes are unusually common or unusually easy to detect. In that case, part of what Webb first interprets as unexpectedly mature galaxy building could instead be a period of rapid central black hole feeding superimposed on young galaxies. The galaxies are not illusions, and the black holes are not separate from them. The point is subtler. A galaxy in the early universe may look more luminous and perhaps more massive, because one of its deepest central processes is contributing strongly to the total light. The result is a young cosmos that can seem more heavily populated by large stellar systems than it really is if the central engine is not separated from the surrounding galaxy. There is also a calm but important implication for how fast black holes themselves may be growing. NASA's reporting on little red dots frames them as a potential peek into early black hole growth. If many of these compact red sources really are active galactic nuclei, then the early universe is not only forming galaxies quickly enough to be seen by Webb, it is also feeding central black holes efficiently enough to make them visible through their accretion light. This does not mean every early bright source is black hole dominated, and it does not mean the first galaxies are irrelevant. NASA's own wording remains careful, saying researchers are still working to determine the nature of the little red dots and whether their light is dominated by accreting black holes. But the broad direction is now clear. Hidden black hole light is not a minor correction at the edge of the data. It is one of the main reasons the earliest Webb observations require reinterpretation. This helps explain why the early universe mystery becomes more disciplined rather than less. At first, the bright galaxies seem simply too massive too soon. Then some of the brightness is traced to black holes, and the mass estimates become less extreme. A careless reading might say the puzzle is therefore gone. NASA does not say that. NASA says the standard model is not in crisis, but also says astronomers are still seeing more galaxies than predicted. Hidden black hole light removes part of the first alarm while leaving a quieter tension behind. The black holes explain some of the excess brightness, but not all of the broader statistical mismatch between observation and expectation. In that sense, the discovery of strong early accretion light is both an answer and a refinement. It solves one layer while exposing the next layer more clearly. So in this region of the story, the early universe light becomes more ambiguous in the most productive scientific sense. It is no longer enough to say that a bright object is a bright galaxy. One must ask how much of the light comes from stars and how much comes from gas spiraling into a central black hole. Observations indicate that many little red dots show the signatures expected from rapidly accreting supermassive black holes, and NASA explicitly identifies hidden black hole light as one reason some early galaxies first appear too big for their age. It remains uncertain how large the black hole contribution is in every individual case, and whether all members of the class are governed by the same balance of starlight and accretion light. What is already clear is that some of the earliest cosmic brightness is not simple starlight alone. A hidden central engine is shining through the young universe, and its light is one of the reasons the first Webb view of cosmic dawn does not add up as easily as astronomers once imagined. The next inward layer of the mystery is not a black hole and not a broad population count. It is the stellar engine inside many of these early galaxies. James Webb begins to show that a large share of the young systems in its deep surveys are not building their visible light in a slow, even, and settled way. NASA reports that almost every single early galaxy studied in one major Webb sample shows unusually strong emission line signatures indicating intense recent star formation. An emission line is a bright feature at a particular wavelength produced when energized gas radiates light. In this case, those lines are a sign that the galaxies contain many hot young stars whose radiation is exciting the surrounding gas. The galaxies are therefore not merely present early. Many of them appear to be in the middle of strong recent bursts of star formation. This matters because a burst is different from steady growth. In a steadily growing galaxy, gas turns into stars at a more moderate ongoing rate, and the light builds up over time in a smoother way. In a bursty galaxy, by contrast, the recent past dominates the observed light. A comparatively short period of vigorous star formation can produce many hot, massive stars at once, and those stars pour out intense ultraviolet light that then shifts into the infrared by the time it reaches Webb. The surrounding gas glows strongly in emission lines, and the galaxy can look more luminous than a calmer system with the same long-term average growth. NASA's Webb release says these early galaxies are very good at creating hot, massive stars. This is an important refinement of the mystery. Some of the brightness that first seems difficult to understand may not require an impossibly old population of accumulated stars. It may instead reflect galaxies caught during intense recent episodes of stellar production. The evidence for this comes largely from spectroscopy. NASA explains that the JADES team uses Webb's near-infrared spectrograph to look for signatures of star formation and finds them in abundance. Spectroscopy matters here because images alone show brightness and rough shape, but spectra show how that brightness is being produced. Strong emission lines indicate gas that is being ionized by young stars. The younger and hotter the stars, the stronger and more distinctive some of these lines can become. In the early universe, where galaxies are chemically less enriched than later systems, and where short, intense growth phases may be common, this effect can be especially pronounced. The light therefore carries a message not just of existence, but of timing. Many of these galaxies are not simply full of stars, they are full of very recent stellar activity. That timing helps explain why the early galaxy problem becomes more subtle after Webb. A galaxy dominated by hot young stars can shine strongly without already having built up an enormous long-term stellar mass. The distinction is easy to miss if one treats the light as though it comes from a calmer mixed-age population. NASA's early universe burst report says these galaxies likely experience star formation in fits and starts, or bursty episodes, and that this can help explain why they are brighter than expected. In other words, the brightness may say less about how many generations of stars have already formed over a long period, and more about how many massive stars have formed recently in a short, concentrated interval. A brief burst can make a young galaxy conspicuous very early, even before it has had time to grow into something more mature by later standards. This does not eliminate the mystery. It changes its scale. The problem is no longer simply that galaxies look too big too soon. It is that the early universe may be producing visible bursts of star formation more readily, more often, or more efficiently than many pre-Webb expectations emphasize. NASA's release frames this as a major clue to why the galaxies are surprisingly bright. If recent bursts dominate the light, then some of the original tension softens. But the softened version still leaves an important question behind. Why are so many young galaxies caught in such intense stellar episodes so early in cosmic history? The answer is not yet final. Webb shows the signature of the burst very clearly, but the deeper reasons for their frequency and intensity remain part of the continuing investigation. There is also a broader historical significance to this result. Before Webb, astronomers already know that some small galaxies in the younger universe can form stars in short, vigorous episodes. What Webb does is push that picture much farther back into time, toward the era when galaxies are first becoming common. NASA says the telescope is now finding these strong emission line signatures in galaxies from the first few 100 million years after the Big Bang. That means bursty star formation is not merely a later side path in galaxy evolution. It may be one of the basic modes by which the earliest visible galaxies first make themselves known. The first luminous systems may be appearing to Webb not as quiet, gradual assemblers, but as young star factories briefly burning with unusual efficiency. The phrase crackled with bursts, which NASA uses in its headline, is vivid but still scientifically grounded. It captures the idea that the early cosmos is not smoothly and evenly lighting up everywhere at once. Instead, it may be full of short, intense episodes scattered across many small young galaxies. These episodes do not need to last long on cosmic timescales to matter observationally. A galaxy seen during such a phase can dominate a deep image relative to a calmer neighbour. This also helps explain why early survey fields begin to feel unexpectedly rich. Webb may be sampling a population in which many systems are temporarily overperforming in visible light because they are passing through recent starburst phases. The galaxies are real, their light is real. But what the light means about their long-term maturity is more complicated than the first brightness alone suggests. So in this region of the story, the early universe mystery becomes a problem of rhythm. The galaxies are not only bright, many are bright in a specific youthful way, marked by strong emission lines and hot massive stars that point to intense recent star formation. Observations indicate that bursty growth can account for part of the surprise by making small young systems look unusually luminous for their age. It remains uncertain exactly how common, how brief, and how efficiently fueled these bursts are across the whole early galaxy population. What is already clear is that Webb is not merely seeing a young universe populated by calm miniature galaxies. It is seeing a young universe in which many early galaxies appear to be forming stars in sudden, powerful waves. And that bursty light is one of the reasons the first cosmic structures seem not to add up, as simply as astronomers once expected. Around some of the early galaxies James Webb reveals, there is more than starlight and more than the surrounding neutral fog of the young universe. There is also a local feeding ground, a broad supply of raw gas gathered around the galaxies themselves. NASA reports that researchers identify 3 galaxies from when the universe is only about 400 million to 600 million years old, and find that these systems are surrounded by unusually large amounts of dense gas. The gas is thought to be almost purely hydrogen and helium, the earliest elements formed in the cosmos. This detail matters because it places the galaxies in a setting that is not yet strongly enriched by many generations of heavier elements. The young systems are therefore not only shining early, they are also embedded in reservoirs of very primitive material close to the original chemical simplicity of the early universe. This surrounding gas changes the picture of what an early galaxy is. It becomes harder to imagine these galaxies as isolated islands that simply gather themselves from what is already inside them, NASA quotes members of the Discovery team saying that this work moves astronomy away from a picture of galaxies as isolated ecosystems. Instead, at this stage of cosmic history, galaxies appear intimately connected to the intergalactic medium, with its filaments and structures of pristine gas. That phrase is important because it makes the outer environment local and physical. The gas is not only a distant background medium spread evenly through space, it appears to be gathered around the galaxies in a way that directly affects their growth. The early galaxy is not sealed off from its surroundings, it is being fed by them. NASA's report also says that this gas is cold and neutral. Cold here is relative to the surrounding high-energy processes of galaxy formation, not to earthly weather. Neutral means that the hydrogen is still largely in the state where its electron remains bound to its proton. In the era of reionization, this matters because neutral hydrogen is both the raw material for future stars and the same kind of material that makes parts of the early universe opaque to energetic light. The feeding gas around these galaxies is therefore not only fuel, it is part of the same larger young universe medium that still has not been fully transformed into the clearer cosmic space seen later in history. The galaxies live inside their fuel supply while that supply still belongs to a partially opaque cosmic age. What Webb detects is not simply a vague halo. NASA says the telescope's instruments are sensitive enough to detect an unusual amount of dense gas surrounding these galaxies, and the associated spectra show that light from the galaxies is being absorbed by large amounts of neutral hydrogen gas. The researchers infer that the gas must be very widespread and must cover a very large fraction of each galaxy. This is a remarkable observational step because it means Webb is not only finding the galaxies themselves, it is beginning to reveal the material around them in a way that speaks directly to how the galaxies will continue to grow. The young systems do not appear to be finished structures. They appear to be still assembling, still drawing matter inward, and still surrounded by the fuel that will shape what they become. That raw material is expected to turn into stars only gradually. NASA says this gas will likely end up fueling the formation of new stars in the galaxies, and that it will go on to cool, clump, and form new stars. The phrasing is calm, but the physical meaning is rich. Gas does not become a galaxy merely by existing nearby. It has to lose energy, gather more tightly, and condense into denser regions before star formation can proceed. The large reservoirs therefore represent possibility rather than completion. They're a sign that some early galaxies may look bright not because they have already converted most of their available material into stars, but because they are caught in the middle of a larger process in which much of the fuel still remains outside the main, visible stellar body. The galaxies are bright now, but they may also still be at an early stage of their own construction. This helps soften one part of the wider early universe tension. NASA notes that by matching Webb's data to models of star formation, the researchers find that these galaxies primarily contain young stars, and that the presence of large gas reservoirs suggests the galaxies have not had enough time to form most of their stars yet. This is an important adjustment to the mystery. A bright early galaxy does not necessarily have to be interpreted as one that has already completed an improbably large share of its stellar growth. It may instead be a galaxy in a youthful active state, surrounded by a great deal of still unconverted gas. In this view, some of the apparent maturity gives way to a different picture, one in which early visibility and incomplete assembly coexist. The galaxy looks prominent, but a great part of its future mass may still be waiting outside the visible stellar center. The image becomes even more interesting when placed beside the broader findings on bursty star formation. NASA has already reported that many early galaxies show strong emission line signatures indicating intense recent star formation, and the gas reservoir discovery provides a natural physical setting for that behavior. A galaxy surrounded by abundant dense hydrogen and helium has access to the raw ingredients needed for repeated or continuing star-forming episodes. This does not prove that every burst is driven in the same way, and it does not eliminate the role of black holes or other processes, but it does make the early galaxies feel less like sealed finished systems and more like nodes in a larger flow of matter. Their brightness can be linked not only to what they already contain, but also to what they are still receiving from outside. There is also a larger cosmic significance in the fact that these feeding grounds are found so early. NASA's release says the 3 galaxies are observed when the universe is only 400 million to 600 million years old. At that age, every large reservoir of neutral gas still belongs to a cosmos in transition. A cosmos where galaxies are helping to reshape their surroundings, even as the surroundings continue to feed them. The galaxies are like bright islands, as the researchers say, in a sea of otherwise neutral opaque gas. But the image is more dynamic than an island in an ordinary sea. The sea itself is part of the galaxy's future. The surrounding gas is not only an environment to shine through, it is matter that may eventually fall inward, thicken, cool, and become stars. This makes the earliest visible galaxies feel less self-contained and more porous. They are places where the outer universe is still entering the galaxy. So in this region of the story, the mystery becomes a question of supply. The early galaxies are bright, some are bursty, some host hidden black hole light, and some seem unexpectedly developed. Yet around at least a few of them, Webb now reveals large reservoirs of dense, mostly primordial gas. Observations indicate that this gas is widespread, closely associated with the galaxies, and likely to fuel future star formation. It remains uncertain exactly where all of the gas sits relative to the galactic centers, how much of it is already enriched by heavier elements, and how common such large feeding reservoirs are across the broader early galaxy population. What is already clear is that the first galaxies are not simply forming out of what they already have. Some of them are still being supplied from outside, fed by the surrounding young universe in a way that gives their early brightness a more physical and less isolated meaning. Around the earliest visible galaxies, the darkness of the young universe does not lift everywhere at once. It opens in pockets. NASA describes this phase by saying that relatively tiny galaxies drive reionization, clearing massive regions of space around them, and that these transparent bubbles grow larger over time and eventually merge until the universe becomes broadly transparent. This means the space around an early galaxy is not just background. It can be physically transformed by the galaxy's own radiation. The outer fog of neutral hydrogen, so important in the earlier sections of this story, is not merely something the galaxies shine through. It is something they begin to erode. A bubble in this context is a region of ionized gas surrounding a source of energetic light. The region is not empty, and it is not a shell like a soap bubble. It is a volume in which the hydrogen has been altered enough that light can pass more freely. In the young cosmos, such clearings are among the first local signs that the universe is changing from opaque to transparent. NASA's early Webb work on reionization emphasizes how surprising the scale of these clearings can be. The agency says the transparent gas regions are gigantic compared with the galaxies themselves, using the image of a pea suspended inside a hot air balloon to convey the contrast. That comparison is useful because it shows how a small luminous source can have a much larger effect on the surrounding intergalactic medium. The visible galaxy may occupy only a tiny central part of the region, while the ionized bubble around it extends far beyond the stellar body. This makes the early universe scene feel less like isolated bright points, set in a uniform fog, and more like many small engines, each reshaping a substantial local volume of space. The first galaxies are therefore not passive lights. They are active clearers of their surroundings. In the language of the mystery, this matters because it offers one route by which unexpectedly early galaxies might become visible even while the wider cosmos remains largely neutral. A galaxy does not need the whole universe to be transparent. It only needs enough surrounding space to be cleared along or near the line of sight. This process becomes especially vivid in the case of JADES-GS-Z 13-1. NASA reports in March of the year 2025 that this galaxy is observed just 330 million years after the Big Bang, and shows bright hydrogen emission known as Lyman alpha. That is surprising because the early universe at that time is thought still to contain a thick fog of neutral hydrogen that should usually absorb or scatter such light before it can travel freely. NASA says the observation suggests the galaxy is mysteriously clearing the fog around it. The same story explains that researchers conclude the galaxy has formed a large bubble of ionized hydrogen around itself. This is a stronger statement than simply saying rionization exists somewhere in the era. It points to a specific early galaxy that appears already to have made its own transparent neighborhood at a time earlier than many researchers once expected for such a clear local opening. The consequence is quiet but profound. If a galaxy only 330 million years after the Big Bang can produce a bubble large enough for Lyman alpha light to escape, then the onset of transparency in at least some places is happening very early. NASA's report and the associated Nature summary both frame this as evidence that rionization may have begun earlier than previously thought, at least in local regions around certain galaxies. This does not mean the entire universe is already transparent at that age. The broader process still takes hundreds of millions of years more to complete. It means instead that the first clearings may begin in earnest earlier, or under more favorable local conditions, than many simplified timelines suggest. The early clearing of space therefore becomes one of the reasons Webb's view feels difficult to reconcile with older expectations. The telescope is not only finding early galaxies, it is finding signs that some of them are already opening channels through the cosmic fog. NASA's June 2023 result adds a broader population perspective to this picture. In that work, the agency says Webb proves galaxies transform the early universe and identifies relatively tiny galaxies as the drivers of reionization, clearing massive regions of space around them. This is important because it shifts the emphasis away from only the brightest or rarest record galaxies. The work suggests that numerous small galaxies can collectively do much of the clearing. The bubbles are local at first, then expand, overlap, and merge. The early universe becomes transparent not because one giant source switches on everywhere, but because many galaxies gradually punch holes in the fog until the holes join. The mystery, therefore, has two scales at once. One is the striking individual case, like JADES-GS-Z 13-1. The other is the broader demographic picture in which many small galaxies are doing the slow cumulative labor of cosmic clearing. There is still uncertainty in the details. NASA's report on JADES-GS-Z 13-1 says the exact source of the ionizing radiation is still not completely settled. The strong ultraviolet output may come from intense star formation, from a growing black hole, or from some combination of the two. This uncertainty matters because it affects how astronomers model the size and speed of bubble growth around the earliest galaxies. A galaxy dominated by very hot young stars may clear its surroundings differently from one in which a central black hole contributes heavily to the ionizing light. What is already secure is the existence of unexpectedly early transparent gas around at least one such galaxy, and the broader Webb evidence that small galaxies can carve out enormous ionized regions around themselves. What remains uncertain is the exact balance of physical engines doing the clearing in each case. So in this region of the story, the early universe mystery becomes a matter of local transparency. Space around the first galaxies is not uniformly dark or uniformly opaque. It is being opened in expanding regions by the galaxies themselves. Observations indicate that these transparent bubbles can be very large compared with the galaxies at their centers, that many small galaxies likely contribute to the process of reionization, and that one galaxy seen only 330 million years after the Big Bang already appears to have cleared a surprisingly early bubble around itself. The broader cosmic fog has not yet fully lifted, but in some places the lifting has clearly begun. That is what makes this layer of the mystery feel so precise. The young universe is not only producing early galaxies, it is already allowing some of them to open windows through the darkness around them. At this stage of the mystery, the outer environment, the early bubbles, the bright galaxies, the little red dots, the hidden black holes, and the bursty star formation all lead toward one calm requirement. The galaxies must be measured, not merely noticed. In the early days of a new telescope, deep images naturally produce many candidates. Some are likely to be exactly what they seem, and some are not. A faint red source in an infrared image may be a truly distant galaxy, but it may also be a nearer object whose light is altered by dust or by some other complicating effect. This is why the early universe mystery cannot rest on images alone. NASA explains that astronomers first use Webb's near-infrared camera, called NIRCam, to search for faint galaxies that are visible in the infrared, but whose light appears to cut off at a critical wavelength. Then they use Webb's near-infrared spectrograph, called NIRSpec, to measure each galaxy's redshift and reveal the properties of the gas and stars in these galaxies. The mystery meets measurement at the spectrum. Science, NASA, Gov. A redshift is the stretching of light to longer wavelengths because the universe expands while the light is traveling. The farther a galaxy is, the more strongly its light is stretched. In practice, this means astronomers can use the amount of redshift to infer how far back in time they are seeing the object. NASA's description of the JADE's work is especially clear on this point. The team uses NIRSpec to collect the light from hundreds of faint galaxies and study the patterns imprinted on each spectrum by the atoms in those galaxies. This yields a precise measurement of each galaxy's redshift. Precision matters because a candidate early galaxy is one thing, while a spectroscopically confirmed early galaxy is another. The first belongs partly to probability. The second belongs much more firmly to observation, science, NASA, Gov. The initial image-based selection already carries some physical meaning. NASA says the JADE's team searches for sources that are visible in the infrared, but whose spectra abruptly cut off at a critical wavelength. That cutoff is not arbitrary. It reflects the effect of intergalactic hydrogen on very distant light. In a young universe galaxy at high redshift, light shortward of a certain wavelength is strongly absorbed or scattered by hydrogen along the line of sight, while longer wavelengths continue to reach the telescope. This creates what astronomers often call a break, an abrupt drop in the observed spectrum. In simple terms, the galaxy looks present in some infrared bands and absent in others. That pattern makes it a strong candidate for great distance, but the actual redshift still has to be confirmed by spectroscopy. The image points, the spectrum decides, science. NASA, Gov. NASA's December 2022 account of JADES shows how powerful this step is. The team takes a single and near-spec observing run lasting 3 days and totaling 28 hours of data collection. From that one set of observations, the researchers collect the light from 250 faint galaxies and obtain the faintest infrared spectra yet taken at the time of the report. Among these, 4 galaxies are spectroscopically confirmed at redshifts above 10, including 2 at redshift 13, corresponding to a time when the universe is about 330 million years old. This is one of the moments when the early universe puzzle changes character. The problem no longer rests only on photometric candidates, meaning candidates inferred mainly from colours in images. It begins to rest on spectroscopic confirmation. The galaxies are not merely plausible. They are measured into place. Science. NASA. Gov. The same logic applies at the record frontier. NASA's May 2024 report says that JADE's GS Z140 is observed with ENIASPEC for almost 10 hours, and that when the spectrum is first processed, there is unambiguous evidence that the galaxy is indeed at a redshift of 14.32. That phrase unambiguous evidence is especially important in a field where some of the first results appear almost too surprising to trust at first glance. A record galaxy this early could easily invite skepticism. But spectroscopy answers that skepticism in the language astronomers trust most at these distances. It does not simply show that the source is red. It shows where its spectral features fall, how far the cutoff has moved, and therefore how much the light has been stretched by cosmic expansion. In the case of JADE S-G S-Z 14-0, the spectrum does not merely suggest a record, it secures it. Science. NASA. Gov. Sometimes the spectrum does more than confirm distance. NASA's March 2025 report on JADE's GS ZR13-1 shows this especially well. The galaxy is first discovered with deep NIRCam imaging, but the later spectrum confirms a redshift of 13.0 and then reveals something unexpected, a distinctly bright wavelength of light known as Lyman alpha emission from hydrogen. This is a powerful example of why spectra matter so much. An image can reveal a candidate ancient galaxy. A spectrum can turn the same object into a physical story. In this case, the spectrum confirms the distance and also reveals that the galaxy shows stronger hydrogen emission than many astronomers think likely at such an early stage, when the surrounding universe should still be thick with neutral hydrogen fog. The spectrum therefore acts as both ruler and witness. It measures the distance and discloses the local conditions. Science. NASA. Gov. This is why the spectral reality checks are so calming. Even when the results remain surprising, they do not erase the mystery. They make it narrower and more trustworthy. A candidate selected from images may later be revised, a source whose redshift is spectroscopically secured, whose hydrogen features are identified, and whose light can be decomposed into stellar and gaseous contributions becomes much harder to dismiss. NASA's description of the JADE's process emphasizes exactly this. NIRCam imaging finds the likely targets. NIRSpec then measures redshift and reveals the properties of the gas and stars. The transition is from appearance to diagnosis. It is one of the reasons the current early universe tension remains scientifically serious. The most surprising galaxies are not only bright red smudges on a deep image. In the strongest cases, they are spectroscopically confirmed objects with measured ages and recognizable physical signatures. Science. NASA. Gov. Science. NASA. Gov. So in this region of the story, the mystery becomes more exacting. The early galaxies are first found as infrared candidates in the deep survey images, often by the abrupt cut-off of light at critical wavelengths. Then Webb's spectrograph measures the redshift directly and exposes the lines and breaks written into the light by hydrogen, stars, and gas. Observations indicate that this method has already pushed spectroscopic confirmation beyond redshift 10, up to redshift 14.32, and has shown unexpected hydrogen emission in at least one galaxy seen only 330 million years after the Big Bang. It remains uncertain how every new candidate will fare under future spectroscopic scrutiny, because the frontier keeps moving and the sources remain faint. What is already clear is that the early universe mystery is not resting on image impressions alone. It has passed through the quiet discipline of spectra, and it is still there. By this point in the mystery, the question is no longer whether James Webb has really seen distant galaxies, or whether some of them are unexpectedly bright, or whether black holes and bursty star formation complicate the first impressions. Those points now belong to observation. The deeper question becomes theoretical. What has to change in the picture of early galaxy growth so that the observations and the model can live together without forcing a collapse of the larger cosmological framework? NASA's own summary of the situation is careful and revealing. It says there is no crisis for the standard model of cosmology, but it also says a less thorny problem remains. That phrase marks the present stage of the field. The first shock has softened, yet the need for repair has not gone away. The model bends, it does not simply break. The standard model in this context means the broad modern picture in which the universe begins hot and dense, expands over time, and forms structure gradually through the growth of dark matter halos, the cooling of gas, and the formation of stars and galaxies within those halos. This framework has been successful across a great range of observations, from the expansion history of the universe to the large-scale distribution of matter. Webb's early galaxy results do not erase that success. NASA says the early galaxies are not so massive that they break the universe, and that after better analysis some of the first alarming estimates come down substantially. The tension, therefore, does not arise because the whole framework has suddenly failed. It arises because one part of the framework, the practical expectation for how quickly visible galaxies become common and luminous, appears to need adjustment. That adjustment begins with interpretation of light. NASA's August 2024 report explains that some early galaxies first appear too massive because black holes make them seem brighter and bigger than they really are. Once those compact sources, including many little red dots, are treated more carefully, the inferred stellar masses of some systems drop. This is already a theoretical repair, because it changes the bridge between observation and model. The galaxies themselves have not changed. The way their brightness is translated into stellar mass has changed. A model does not fail only when its equations are wrong. It can also seem to fail when the observations are being connected to the wrong physical interpretation. Part of the Webb tension is now understood in exactly that way. The first bridge from light to mass is too simple, and the bridge has to be rebuilt more carefully. Even after that repair, NASA says astronomers are still seeing roughly twice as many massive galaxies in the early universe as some standard model expectations predict. This is the part that keeps the mystery alive. If the first crisis were only a matter of contaminated brightness from black holes, then the story would have become mostly procedural. Correct the estimates, and the problem disappears. NASA's wording shows that this is not what happens. The strongest version of the problem softens, but the census still remains high. There are still more substantial galaxies than many simulations and pre-Webb expectations produce. The model, therefore, does not need abandonment, but it does appear to need recalibration in the details of very early galaxy assembly. One likely area of repair is star formation itself. NASA's Webb reporting says many early galaxies show unusually strong emission lines and appear very good at creating hot massive stars. If that is common in the first few 100 million years, then galaxies can appear brighter earlier without needing impossibly large old stellar populations. In theoretical terms, that means the efficiency and timing of early star formation may need to be adjusted. A galaxy may convert cold gas into visible massive stars faster, or in more concentrated bursts, than many older models emphasize. This does not overturn the idea of gradual structure formation. It changes the pace and visibility of the earliest luminous phases inside that structure. The framework stays, but the first chapters may be more active than previously assumed. Another area of repair lies in the role of black holes. NASA's reports on little red dots and early galaxy masses both point toward rapidly accreting supermassive black holes as an important contributor to early brightness, if active galactic nuclei are common enough in the young universe. Then some of the light counted as galactic starlight in first analyses must be reassigned. This affects not only mass estimates but also the expected visibility of young systems in deep surveys. A galaxy with a growing black hole can enter the observed sample earlier and more dramatically than a purely stellar system of the same mass. Theory then has to allow not just for early stars, but also for early central engines that can change how young galaxies look to a telescope. This is not a rejection of earlier galaxy formation theory so much as an enlargement of it. Gas supply is another likely part of the repair. NASA reports that some early galaxies are surrounded by unusually large amounts of dense gas made mostly of hydrogen and helium, and that this gas will likely cool, clump, and fuel new star formation. If such feeding reservoirs are common, then early galaxies may grow and brighten more efficiently than models assuming more limited local fuel would suggest. In that case, the problem is not that the universe forms galaxies impossibly fast. It is that the galaxies visible to Webb may be sitting in especially favorable conditions for rapid early growth. Theory would then need to represent more accurately the connection between young galaxies and the gas-rich environments around them. The galaxies are not isolated islands, they are parts of flowing systems. There is also a methodological repair underway in how the observational sample itself is treated. Deep fields do not simply reveal one kind of source, they reveal extended stellar systems, compact red dots, black hole-dominated nuclei, bursty star-forming galaxies, and systems caught in different stages of reionization. If all of these are folded too quickly into one broad category of early galaxies, the theoretical comparison becomes unfair. NASA's recent summaries show that the field is already separating these categories more carefully. This is one reason the current tension feels more trustworthy than the first headlines. It is being refined rather than defended at all costs. Theories are not only adjusting to the data are also being sorted into more meaningful physical classes before they are compared with theory. So this layer of the story is one of repair rather than ruin. The earliest Webb results make the young universe seem too bright and too developed too soon. Later work shows that some of that impression comes from black hole light, some from bursty young stars, some from how mass is inferred from brightness, and some perhaps from early galaxies drawing on rich gas reservoirs more effectively than many models assume. Observations indicate that the strongest version of the crisis fades, but that a real mismatch remains in the number of substantial galaxies seen very early. It remains uncertain exactly how much of the remaining tension will yield to better modeling of star formation, black hole growth, gas accretion, and sample selection. What is already clear is that Webb has not simply broken the model. It has forced astronomers to repair the parts of the model that connect first light to first galaxies, and those repairs are still underway. At the innermost layer of the mystery, after the horizon light, the fog of rionization, the deep survey fields, the record galaxies, the bright population, the little red dots, the hidden black holes, the stellar bursts, the gas reservoirs, the early bubbles, the spectra, and the repaired theory have all been taken into account. One quiet fact remains. James Webb still seems to show an early universe that becomes visible a little too quickly and a little too effectively for many earlier expectations. NASA's own summaries now describe the situation with unusual balance. The first dramatic claim that the early galaxies are impossibly massive softens after astronomers treat their light more carefully. Yet NASA also says that even after these revisions, there are still roughly twice as many massive galaxies in the early universe as some standard model expectations predict. This is the part that still does not add up. The discrepancy is no longer wild enough to sound like collapse, but it is still persistent enough to resist dismissal. That persistence matters because science can often absorb one isolated surprise. It can usually absorb a first round of overestimation as well. What gives the Webb mystery its staying power is that it survives correction. Some of the light comes from accreting black holes rather than stars alone. Some galaxies are brighter because they are caught in intense recent bursts of star formation. Some may sit inside especially favorable gas-rich environments that help them grow quickly. Some sources belong to the new class of little red dots and should not be counted as ordinary stellar systems in the simplest way. All of this narrows the problem, but after the narrowing, the count remains high. The early universe still appears to contain more substantial visible galaxies than many pre-Webb models comfortably anticipate. The remaining tension, therefore, belongs not to a single mistake, but to the combined outcome of several revised interpretations that still leave a mismatch behind. One possible answer is that early star formation is simply faster or more efficient than many older assumptions allow. NASA reports that almost every early galaxy in one major Webb sample shows strong emission lines indicating intense recent star formation, and that these galaxies appear very good at creating hot, massive stars. If this is common, then the first galaxies become visible more easily and more often than slower growth pictures suggest. In that case, the early universe may not be violating the standard cosmological framework. It may be using that framework in a more vigorous way at small scales than many astronomers had expected before the new data arrived. The galaxies would still form through the growth of structure inside dark matter halos. But the conversion of gas into luminous stars would proceed in a way that makes the early sky brighter and more crowded than earlier models emphasize. Observations indicate that this possibility is now part of the serious explanation, though it is not yet enough on its own to settle the matter. Another possible answer is that black hole growth turns on very early and contributes more strongly to visibility than many simple galaxy growth forecasts assume. NASA's reports on little red dots say many of these compact red sources likely host accreting, supermassive black holes. And the same NASA analysis of the early mass problem says black holes in some galaxies make them appear much brighter and bigger than they really are. If active galactic nuclei are more common in the first billion years than previously thought, then the young universe can look more mature in light than it really is in stars. This would not remove the galaxies, but it would change what part of the galaxies is doing the shining. The remaining uncertainty lies in scale. It is not yet fully known how much of the early brightness budget should be assigned to black hole accretion across the whole population, and how much should still be attributed to stars. The observations strongly suggest that black holes matter early. They do not yet show that black holes explain everything. A third possibility lies in the supply of gas itself. NASA reports that some early galaxies are surrounded by unusually large amounts of dense gas composed mainly of hydrogen and helium, and that this gas is likely to cool, clump, and fuel future star formation. If many early galaxies sit in such rich feeding grounds, then they may brighten sooner and continue forming stars more actively than models with more limited local fuel would predict. This possibility changes the tone of the puzzle in an important way. The galaxies may not be overachieving by magic. They may simply be growing in environments where the raw material arrives efficiently and remains available. Still, the present evidence is not broad enough to prove that every bright early galaxy enjoys the same abundance of fuel. Observations indicate that at least some do. It remains uncertain how representative those gas-rich cases are across the full early population. There is also the question of ionization itself. NASA's Webb reports say relatively tiny galaxies can clear massive regions of space around them, and that one galaxy only 330 million years after the Big Bang appears already to have formed a large ionized bubble around itself. If transparent bubbles form earlier or more efficiently than many simplified pictures suggest, then some early galaxies may be easier to detect because they are not trapped inside a uniformly opaque cosmos. In that case, part of what does not add up is not the galaxies alone, but the speed and patchiness with which the surrounding fog is being cleared. Light reaches the telescope not only because galaxies exist, but because in some places the medium around them has already become surprisingly permissive. This again narrows the mystery without ending it. A galaxy can be made easier to see by its bubble, but the bubble itself then becomes part of the same early efficiency problem. So the remaining puzzle is not one sharp contradiction. It is several moderate tensions laid on top of one another. There may be faster star formation, earlier black hole growth, richer gas supply, and more efficient local clearing of the early intergalactic medium. Each of these helps. None of them has yet closed the case completely. NASA's wording remains the best guide to the present moment. There is no crisis for the standard model of cosmology, but a less thorny problem remains. That sentence reflects a field that is adjusting rather than collapsing. The early universe Webb reveals is still governed by the broad framework of cosmic expansion and structure growth, yet the details of how the first luminous galaxies form, brighten, and become visible are being revised in real time. Observations indicate that the mystery has narrowed. It remains uncertain which combination of revised galaxy physics will account for the full remaining excess. What's already clear is that James Webb has not found one impossible object that overturns everything. It has found a young universe whose first visible structures are still teaching astronomers how quickly cosmic light can gather itself in the dark. The distant light settles into order. James Webb looks across almost the full age of the universe and finds that the first visible galaxies arrive sooner, brighter, and in greater numbers than many earlier expectations comfortably allow. Some of the first alarm softens. Part of the light comes from growing black holes. Part of it comes from short, intense bursts of star formation. Some galaxies seem to sit inside rich reservoirs of gas, still gathering fuel from the young cosmos around them. Some appear to open clear local bubbles in a universe that is not yet broadly transparent. The mystery becomes narrower, but it does not disappear. What remains is quieter than the first headlines and stronger than a simple mistake. The earliest visible universe is not empty and hesitant. It is active. It forms stars quickly. It grows black holes early. It clears surrounding hydrogen sooner in at least some places. It produces real galaxies whose light can be measured, tested, and confirmed. Yet even after care is taken with the brightness, the masses, the spectra, and the compact red sources, the count of substantial early galaxies still seems higher than many older models prefer. So the picture does not break. It adjusts. The broad framework of cosmic history still holds, but the first luminous chapters seem more efficient, more crowded, and more restless than astronomers once imagined. The young universe looks less like a slow, dim beginning and more like a place where structure gathers itself quickly out of darkness. In that way, the mystery remains gentle. It is not a contradiction that destroys understanding. It is a tension that sharpens it. The first galaxies do not simply appear, they arrive with enough force to teach the telescope's builders and the theorists who follow them that the early cosmos may have learned how to shine sooner than expected. The farthest light is still ancient, still faint, still stretched by expansion. But inside it, the young universe already seems busy, and that quiet excess is what still does not fully add up.